Of all the titanic forces that sculpt our universe, which is the most profound? Is it gravity, the tireless architect patiently gathering dust into stars and stars, into the breathtaking spiral cities we call galaxies? Is it the raw, explosive power of a supernova seeding the cosmos with the very elements of life? Or could it be something far more subtle, far more pervasive? Could the greatest force in creation be nothing at all? For millennia, we have told our cosmic story as a tale of light, a story of things, of matter. We look out into the deep and see a universe overflowing with brilliance, an intricate luminous tapestry woven from 100 billion galaxies. This is the cosmic web, the grandest structure in existence. Imagine it not as a random scattering of points, but as a living network, a celestial nervous system stretching across unimaginable scales. Galaxies are not lonely islands, they are citizens of a bustling, interconnected metropolis. They flow along immense, invisible rivers of dark matter congregating in shimmering filaments that span hundreds of millions of light years. These filaments are the superhighways of the universe, channels of gravitational influence guiding the flow of cosmic history. Where they intersect, they form dense, frenetic hubs of activity. These are the great clusters, the galactic megalopolises home to thousands of galaxies locked in a chaotic, beautiful dance. Our own Milky Way is but a single modest home in a quiet suburb of the Virgo supercluster, a sprawling congregation of light and life. And even Virgo itself is just one tributary, flowing into a vaster ocean of galaxies, a continent of matter we have named Laniakea, the immeasurable heaven. Everywhere we look, we see this pattern of connection of structure. Gravity's patient hand has spun a web of staggering complexity, pulling matter together, building, always building. From the smallest asteroid to the most colossal galactic cluster, the universe seems driven by an undeniable impulse to congregate, to form, to be. This is the universe as we have always known it, the one we have celebrated in art and science, a cosmos of presence, a cosmos defined by what is there. It is a comforting thought, this vision of a full and vibrant reality. But it is only half the story. It is an illusion born of our perspective from a brilliantly lit corner of existence. To truly understand the universe, we must let go of our terrestrial bias for substance. We must perform an act of cosmic imagination. We must pull back. Further and further we retreat from our familiar home. The Milky Way shrinks to a swirl of diamond dust. The local group becomes a small, intimate gathering. The Virgo supercluster, once a sprawling empire, resolves into a bright knot of light. As we pull back further, a new and startling picture begins to emerge. The brilliant incandescent filaments of the cosmic web, those rivers of light, begin to look fragile, almost tentative. They are revealed for what they truly are: not the substance of the universe, but luminous traceries stretched across something else, something vast, dark, and utterly dominant. Stretching between the filaments, we discover the deserts, the great yawning chasms of the cosmos. These are the cosmic voids. They are the silent majority of the universe. For every galaxy blazing in a star-spangled filament, there are volumes of space, hundreds of millions of light years across, that are almost entirely bereft of matter. These are not simply empty patches of space in the way we might imagine. They are the result of a cosmic battle fought over billions of years. In the universe's infancy, matter was spread almost perfectly evenly, but almost is the most important word in cosmology. Tiny quantum-scale fluctuations in density meant some regions were infinitesimally heavier. Over eons, gravity, the great accumulator, began to work its magic. The slightly denser regions pulled in more and more material, starving their surroundings. The cosmic web grew stronger, brighter, and more concentrated, but it did so at a terrible cost to the space around it. It acted like a cosmic siphon, drawing matter out of vast regions, leaving them gravitationally impoverished and desolate. The voids are the consequence. They are the spaces in between, the monumental caverns of shadow left behind by the universe's relentless construction project. If the cosmic web is the skeleton of the universe, the voids are the flesh of its emptiness. They make up more than 80% of the volume of the known cosmos. Our entire story, the story of stars, planets, and life, is playing out on the shimmering gossamer threads of a web stretched across an ocean of profound and unsettling nothingness. And this revelation forces upon us a series of questions that cut to the very heart of our existence. What are these places really? Are they truly empty, or do they harbour secrets of their own, perhaps new forms of energy or undiscovered laws of physics that only manifest in a low-density regime? How did they shape our own evolution? Did the sheer scale of the void surrounding our supercluster act as a cosmic cradle, protecting our region from violent intergalactic encounters, allowing life the stable conditions it needed to arise? And what do they tell us about the ultimate fate of everything? As the universe continues to expand, driven by the mysterious force of dark energy, the cosmic web is being stretched thin. The voids are growing, merging, pushing the islands of light further and further apart. Are we witnessing the future of the cosmos in these great deserts? A future where all the light and life huddles together in increasingly isolated clusters, surrounded by an ever-expanding, ever-victorious emptiness. To look into a void is to look into the universe's destiny. Most of these voids, while immense by any human standard, fit within the predictions of our best cosmological models. They are the expected outcome of gravity and expansion playing out over 13.8 billion years. They are large, but they are not monstrous. They are understandable. But science thrives on the anomalies, the outliers, the things that should not be. Because deep within the constellation Eridanus in the southern celestial hemisphere lies a region of space that breaks all the rules. An anomaly so large, so empty and so cold that it defies our neat and tidy explanations. It was first discovered not by what was seen, but by what was missing. Astronomers charting the cosmic microwave background, the faint residual afterglow of the Big Bang, found a patch of the sky that was inexplicably unnervingly cold. This fossil light from the dawn of time carries the imprints of the infant universe with tiny temperature variations that were the seeds of all future structure. Hotter spots would become the great superclusters, cooler spots would remain less dense. But this particular cold spot was far colder and far, far larger than any prediction allowed for. It was a statistical impossibility, an aberration in the baby picture of our universe. For years it remained a maddening puzzle. What could possibly cast such a colossal shadow on the light of creation itself? The search for an answer led astronomers to point their most powerful telescopes at that precise patch of sky to survey the galaxies in that direction. They expected to find a typical distribution, maybe a standard cosmic void. What they found instead was a nightmare for cosmologists. They found a hole in the universe, a region of space almost entirely devoid of galaxies, both normal and dark matter. A chasm of non-being so monumental it dwarfs every other known void. It begins about 3 billion light-years from Earth and stretches for an almost unbelievable distance, more than 1 billion light-years from end to end. To try and grasp that scale is to court madness. Like the fastest thing in existence would take 1 billion years to cross it. You could fit 10,000 Milky Way galaxies side by side in the gap and still have room to spare. The volume of this space is so staggering that it should by all rights contain hundreds of thousands of galaxies. It contains almost none. It is an abyss, the ultimate expression of cosmic emptiness. We call it the Eridanus supervoid, the supergiant void. This is not merely another feature on the cosmic map. This is a direct, profound challenge to our entire understanding of how the universe is built. Our models of cosmic evolution, which work so beautifully almost everywhere else, simply cannot produce a void of this magnitude. It is too big. It is too empty. It is as if we found a desert the size of a continent in the middle of a rainforest, with no geological explanation for its existence. It hints that there is a fundamental piece of the cosmic puzzle we have not yet found. Some unknown force, some exotic physics, or some primordial event that was powerful enough to excavate a billion light-year hole in the fabric of reality. And it connects us directly back to that unnerving chill in the afterglow of the Big Bang. The void's profound emptiness drains energy from the ancient light passing through it, creating the cold spot a celestial fingerprint left by a ghost. The supergiant void is not just an object of study. It is a mystery story written into the very structure of space-time spanning billions of years. It forces us to ask the most uncomfortable questions. Is our theory of gravity incomplete? Is dark energy behaving in ways we cannot yet comprehend? Could this void be the first tangible evidence of something beyond our own universe? Perhaps the gravitational bruise left by an ancient collision with another parallel cosmos. These possibilities are not the stuff of science fiction. They are the very real, very serious hypotheses being considered by scientists grappling with the existence of this cosmic monster. To understand the universe, we must understand its extremes. We have journeyed to the fiery hearts of stars and the crushing singularities of black holes. We have stared back to the dawn of time itself. But now, we must undertake a different kind of journey. A journey not into a place of immense density or energy, but into its polar opposite. We must venture into the heart of the great emptiness. We must cross the threshold into a realm where the fundamental rules of cosmic construction seem to have been suspended, where the tapestry of creation is frayed and torn. This is an expedition into the largest, emptiest, and most mysterious place known to humanity. Our goal is to understand how it came to be what it is made of, and what its haunting existence means for the past, present, and future of everything. The journey ahead will take us to the edge of cosmological theory, pushing the limits of our technology and our imagination. For hidden within this colossal expanse of nothing may lie the most important something we have yet to discover. The story of the universe is not just written in the stars, it is also written in the silence between them, and the supergiant void is screaming. What if the most important thing in the universe is nothing at all? For centuries we held a deeply cherished belief, a cornerstone of our cosmic understanding we called the cosmological principle. It was an idea of profound elegance and simplicity, that on the larger scales the universe is fundamentally the same everywhere. No special places, no privileged directions. It suggested a cosmos that was homogeneous, an evenly woven tapestry of matter and energy stretching out to infinity. From our vantage point on Earth looking out at a sky spangled with countless points of light, this seemed perfectly reasonable. A comforting thought that our cosmic neighbourhood was in essence just like any other. This principle gave us a sense of order, a predictable framework upon which we could build our theories of creation and destiny. It was the grand assumption that the universe in its ultimate majesty played by simple, repeatable rules. We believed we were living in a cosmos that was at its heart uniform, an endless democratic expanse where galaxies were scattered like grains of sand on an infinite shore with no great deserts or towering mountains to break the monotony. It was a beautiful idea, an orderly idea, and as the 20th century dawned, we would discover it was profoundly beautifully and terrifyingly wrong. Our first attempts to map this grand expanse were humble, almost accidental endeavours. Astronomers like Charles Messier, hunting for comets in the 18th century, began cataloguing the persistent fuzzy smudges that littered the sky objects that stubbornly refused to move. His list, a collection of nuisances to be avoided, would ironically become a foundational guide to our own galactic backyard and beyond. These were the first signposts, the initial hesitant pinpricks on a map of unimaginable scale. Following him, the Herschels William and Caroline undertook a far more systematic and ambitious project. With their powerful custom-built telescopes, they conducted a brute force survey of the heavens, charting thousands of these nebulae. Yet even with these growing catalogues, a fundamental question loomed, a debate that would rage for decades. What were these smudges? Were they nascent solar systems, swirling clouds of gas within our own Milky Way? Or were they something far grander? Were they, as some audaciously proposed, entire island universes, galaxies in their own right, floating at unimaginable distances? For a time, the universe we knew was confined, its borders defined by the shimmering band of the Milky Way. The map we were drawing was flat, a two-dimensional projection of the sky, beautiful but lacking all sense of depth, of genuine scale. It was like looking at a photograph of a mountain range and having no way to know which peaks were giants in the distance, and which were merely foothills close by. The true three-dimensional architecture of the cosmos remained utterly hidden from us, locked away in the light from these mysterious objects. The key to unlocking that third dimension, the secret to giving our map its crucial perspective, would come from a seemingly esoteric property of light itself. It arrived with the monumental discoveries of astronomers like Vesto Slipher, and most famously Edwin Hubble. In the 1920s, working at the Mount Wilson Observatory, Hubble, aimed his telescope at these faint spiral nebulae and resolved individual stars within them. By analysing the light of specific pulsating stars, cosmic lighthouses known as Cepheid variables, he could calculate their distance with unprecedented accuracy. The results were staggering, earth-shattering. These were not local gas clouds. They were other galaxies millions, even billions of light-years away. The known universe exploded in size in a single instant. Our Milky Way was not the entirety of creation, but just one island in a cosmic archipelago of hundreds of billions. But Hubble's work revealed something even more profound. When he analysed the spectrum of light from these distant galaxies, he found it was almost universally stretched, its features shifted towards the red end of the spectrum. This redshift was the cosmic equivalent of a siren's wail changing pitch as an ambulance speeds away from you. It was the signature of recession, a clear indication that these galaxies were flying away from us. And the further away a galaxy was, the greater its redshift, the faster it appeared to be receding. This was the observational proof of an expanding universe, a concept that had emerged from Einstein's equations but seemed too bizarre to be true. For astronomers, however, this discovery was more than just a philosophical revelation. It was a practical tool of immense power. Redshift gave us the missing coordinate. It was the cosmic depth gauge. By measuring the colour of a galaxy's light, we could now determine not just its position on the celestial sphere, but its distance from us. We could finally begin to build a true three-dimensional map of the cosmos. The age of cosmic cartography had begun in earnest. The painstaking work of surveying the universe galaxy by galaxy could now reveal its hidden structure. The flat, static portrait of the heavens was about to be torn down, replaced by a dynamic, voluminous, and utterly surprising reality. The initial surveys of the 1950s and 60s seemed at first to reinforce the old ideas of uniformity. As astronomers plotted the positions of thousands of galaxies, the emerging picture looked like a randomly scattered field of points. But a few keen-eyed observers began to notice subtle patterns, hints of something more. Astronomers like Gerard de Vaucouleurs saw evidence that galaxies weren't entirely loners. They seemed to clump together, forming groups and clusters. Our own Milky Way, it turned out, was part of a small gathering called the Local Group, which itself was just an outlying suburb of a much larger metropolis, the Virgo supercluster. These were the first whispers of a grander architecture, a cosmic scaffolding that had until now remained invisible. It was in the 1970s that these whispers grew into a roar. With more powerful telescopes and more efficient ways to measure redshifts, the scale of these surveys expanded dramatically. Instead of plotting a few thousand galaxies, astronomers were now plotting tens of thousands. And as the data points accumulated, the picture sharpened, resolving from a hazy cloud of possibilities into a stunning, undeniable structure. The universe, it was now clear, was not a uniform distribution of matter at all. It was a web, a vast, luminous and intricate network of galaxies, often called the cosmic web. This celestial lacework is the largest structure in existence, a filigree of unimaginable proportions. Dense city-like clusters of galaxies are its major hubs, connected by colossal bridges and walls of galaxies stretching for hundreds of millions of light-years. These are the filaments, the bright shining threads of creation, where matter has been drawn together by the relentless pull of gravity over billions of years. Within these filaments, galaxies are born, they live, they merge and they die. This is where the universe is most alive, a riot of stellar nurseries, blazing quasars and swirling galactic disks. Seeing this structure for the first time was a paradigm shift. It was as if we had spent our entire lives believing the Earth was a smooth, featureless sphere only to suddenly be shown mountains, canyons and continents. The cosmological principle, the idea of a uniform universe, still held true, but only on the very largest, most incomprehensible scales. On any smaller scale, a scale still spanning billions of light years, the universe was anything but homogeneous. It was a place of dramatic topography, of shining superhighways and deep shadowy valleys. And it was the nature of those valleys that would present the next great cosmic mystery. If galaxies were organized into filaments and walls, what lay between them? What was in the spaces this great web enclosed? The initial map suggested they were simply less dense regions, quiet countrysides to the bustling galactic cities. But in the late 1970s, a new survey was being planned that would, by sheer chance, peer into one of these regions with unprecedented clarity. A team of astronomers, including Robert Kirshner, Augustus Umler, Paul Schechter and Stephen Schechtman, decided to embark on a new kind of survey. Instead of sweeping across the entire sky, they chose to drill deep to survey a few small patches of the sky as thoroughly as possible. Their chosen tool was the Multiple Mirror Telescope in Arizona, and their technique was methodical. They would point the telescope at a galaxy, measure its light, calculate its redshift and thus its distance, and then move to the next. One of their target regions was a seemingly unremarkable patch of sky in the direction of the constellation Boötes the Herdsman. They were not looking for anything specific, just gathering data points to help refine the emerging picture of the cosmic web. The work was a slow, meticulous grind. Night after night they would gather photons that had been travelling for hundreds of millions of years. Each successful measurement was another pin in their three-dimensional map. They began by measuring the redshifts of galaxies in their first field. The results were as expected, a smattering of galaxies at various distances confirming the lumpy web-like structure others had seen. They then shifted their focus to a second nearby field and then a third. They were expecting to find more of the same, more galaxies, perhaps part of a different filament or a smaller cluster, but galaxies nonetheless. Instead they found nothing. As they analysed the light from their target area, the redshifts they measured told a strange and unsettling story. They found a handful of galaxies relatively close by. Then, as they looked deeper into space into a region beginning about 600 million light-years away, the galaxies simply vanished. The stream of data points the steady drumbeat of galactic discovery suddenly fell silent. Their map, which should have been steadily populating with new objects, now showed a gaping, unnerving hole. At first they assumed it was a mistake. An error in the delicate instrumentation of the telescope, a flaw in their software, a miscalculation in their complex formulas. Such voids were not theoretically impossible, but a gap of this size seemed ludicrous. The chances of randomly pointing a telescope at such a perfect statistical anomaly were astronomically small, so they recalibrated. They checked their assumptions. They waited for the next clear night and pointed their telescope back at the same patch of sky, half expecting the missing galaxies to suddenly appear, a cosmic mirage dissipated by a more careful look. But they did not. The results were the same. The silence from that region of space was real. They expanded their survey, painstakingly measuring the redshifts of every faint smudge they could find in and around the target area, trying to map the boundaries of this emptiness. Slowly, agonizingly, over months of observation, the true scale of what they had discovered began to dawn on them. This wasn't a small gap between galactic filaments. This wasn't a statistical fluke. They had found a chasm, a cavity in the cosmos so vast it defied all conventional models of the universe's evolution. Based on their initial data from 1981, they estimated this void to be nearly 300 million light-years in diameter. To try and comprehend that scale is to risk madness. If our own Milky Way galaxy were placed at its centre, our nearest galactic neighbour Andromeda, over 2 million light-years away, would still be deep within our cosmic living room. You could fit thousands upon thousands of Milky Way-sized galaxies into this space, yet the team had found only a scant few. It was a volume of space so colossal that it should have contained a rich tapestry of galactic structures, a thriving metropolis of stars and nebulae. Instead, it was a desert. A region where the great engine of cosmic structure formation seemed to have stalled, or perhaps never even started. The publication of their findings sent a quiet shockwave through the astronomical community. They called it, with a scientist's characteristic understatement, the Boötes Void, but its nickname would become far more evocative, the Great Nothing. This monumental discovery did more than just add a new feature to our cosmic map. It posed a terrifying question. How could gravity, the great architect of the universe, allow such a colossal pocket of emptiness to form? What force could have possibly swept a region of space hundreds of millions of light-years across so clean of matter? The Great Nothing wasn't just a place, it was a clue. A monstrous piece of a puzzle we didn't even know we were supposed to be solving, hinting that the story of our universe, its birth, its evolution, and the very forces that governed its structure was far stranger and more mysterious than we had ever dared to imagine. And so with our map of the cosmic web laid bare, we believed we had finally grasped the grand architecture of existence. We saw the filaments, those incandescent rivers of light and matter, flowing between the great glittering cities of galactic superclusters. It was a structure of breathtaking elegance, a celestial tapestry, woven from gravity and time, and we were a part of it. But journey with us now, away from the reassuring glow of those cosmic highways into a region of the sky that seemed at first unremarkable. It lies in the direction of the constellation Bootes the Herdsman, a familiar pattern of stars in our northern sky. In 1981, a team of astronomers led by Robert Kirshner embarked on an ambitious survey, a project to map a slice of this cosmic territory in 3 dimensions. They were pioneers using the redshifts of distant galaxies to gauge their distance painstakingly, adding depth to the flat portrait of the sky. Point by point, galaxy by galaxy, they were building their own section of the universal map. The process was methodical, even tedious, as they aimed their telescope at faint smudges of light one after another, collecting the precious photons that had travelled for hundreds of millions of years. Each successful measurement was another pin in their map, another knot in the luminous web they expected to find. For a time, the work progressed exactly as predicted. Galaxies appeared where they should, clustering in some areas, more sparsely distributed in others, all conforming to the beautiful clumpy logic of the cosmos we thought we knew. Then, as their survey pushed deeper into the constellation's territory, something began to change. It wasn't a sudden dramatic event, but a slow, creeping suspicion, an anomaly that grew with each passing night of observation. The data points, the little pins on their map, started to thin out. Then they stopped altogether. Where their models, their fundamental understanding of the universe screamed there should be galaxies, there was nothing. At first, it had to be a mistake. Perhaps the equipment was malfunctioning, some subtle error in the spectrograph skewing their results. Maybe they had simply hit a statistically improbable, but perfectly natural patch of quiet space, a temporary lull before the next great cluster appeared. They checked their instruments, recalibrated their sensors, and aimed again, pushing even deeper into this silent quadrant of the sky. The result was the same, an unnerving, profound, and ever-expanding emptiness. The silence was no longer a whisper of doubt. It was a deafening roar in their data. They weren't just observing a gap between filaments. They had stumbled upon something else entirely, something their theories had never countenanced. They had found a hole in the universe. This was the moment of confrontation, the instant a single stubborn observation stands up and challenges a century of cosmological consensus. This was the discovery of the Bootes void. To speak of its scale is to risk plunging into madness, for our minds are not built to comprehend such dimensions. Imagine our own Milky Way galaxy, a sprawling metropolis of 400 billion stars, our sun among them, a system so vast that light itself takes 100,000 years to cross it. Now shrink that entire galaxy down in your mind until it is the size of a single grain of sand. At this scale, the Andromeda Galaxy is another grain of sand just a few inches away. Our entire local group of galaxies might fill a coffee cup. The Virgo supercluster, our home complex of thousands of galaxies, would be a sprawling city park. Now, using that same scale, the Bootes void is a chasm in the Earth nearly a quarter of a mile wide. A monolithic sphere of almost nothing, so stupendously large that you could fit thousands upon thousands of city parks like our own Virgo supercluster inside it, and still have room to spare. Its diameter is estimated to be somewhere between 250 and 330 million light-years. Light, the fastest thing in existence, would require 1/3 of a billion years to traverse it from one side to the other. When the first photons of light set out from a galaxy on the far edge of this void, dinosaurs were just beginning to dominate the Earth. By the time that light reached the other side, the dinosaurs were long extinct, and the first ancestors of humanity were just starting to walk upright. The sheer volume of this space is staggering, a geometric monstrosity carved out of the fabric of reality. And yet the true horror of the Bootes void isn't its size, but its desolation. Based on the average density of matter in the universe, a volume of space this large should be teeming with life and light. It should contain, by conservative estimates, well over 2,000 galaxies, perhaps as many as 10,000. It should be crisscrossed by filaments anchored by clusters, a vibrant and dynamic region of the cosmic web. Instead, initial surveys found only 8. Later, more sensitive projects pushed that number up, painstakingly locating a few dozen more, but the conclusion remained inescapable. The Bhuta's void is almost supernaturally empty. If the cosmos were an ocean, this would not be a quiet bay. It would be a region where the water itself had vanished, leaving only a handful of lonely, isolated droplets hanging in an impossible abyss. The discovery was met with profound skepticism throughout the astronomical community. It felt wrong. It violated a core tenet of cosmology, what's known as the cosmological principle, the idea that on the larger scales the universe is essentially the same everywhere. There should be no special places, no vast anomalies that defy the statistical average. Clumps and voids were expected, of course. They are the natural consequence of gravity's patient work. But this was different. This was a statistical outlier so extreme it bordered on the impossible. It was as if you surveyed a rainforest the size of a continent and found only a single solitary tree. You wouldn't question the nature of forests, you would question your survey. So the scientific world did what it does best. It tried to prove Kirshner and his team wrong. Other surveys were launched using different telescopes, different methodologies, all peering into the heart of this supposed emptiness. They probed it with radio waves, scanned it in infrared, seeking the faint hidden glow of galaxies that might have been missed. Each new survey was intended to be the one that would fill in the void, that would reveal the missing galaxies and restore order to the cosmos. And each new survey came back with the same terrifying confirmation. The void was real. The emptiness was genuine. The few galaxies that were eventually found within its borders only served to deepen the mystery. They weren't scattered randomly but seemed to be arranged in a peculiar tube-like structure, a lonely filament of matter running through the heart of the desolation. Who were these cosmic castaways? These 60-some galaxies huddled together for warmth in a sea of cosmic night, a third of a billion light-years wide. They were not anomalies, they were witnesses. Witnesses to a process of cosmic formation so violent and so efficient that it had scoured a region of space vaster than human thought, clean of nearly all matter. This confirmation sent shockwaves through the world of theoretical cosmology. The standard model of structure formation, which relied on the slow, steady pull of gravity, acting on tiny quantum fluctuations from the dawn of time, was suddenly faced with a colossal problem. Gravity is powerful, but it is also slow. Over the 13.8 billion years since the Big Bang, there simply hadn't been enough time for gravity to do this. To form the cosmic web, you can imagine gravity acting like a gentle shepherd, patiently herding loose matter into filaments and clusters. But to create the Bhuta's void, you needed something else. You needed a gravitational snowplow of unimaginable power, an engine of emptiness that could sweep a volume of space thousands of times larger than our own galaxy, almost entirely clean. The elegant gradual models of cosmic evolution couldn't account for it. The timeline didn't add up. It was like finding a fully formed mountain range that had somehow erupted from the flat plains in a single afternoon. The existence of this void wasn't just a new discovery, it was an accusation pointing to a flaw in our most fundamental understanding of how the universe put itself together. So how could it be? How do you create a pocket of nothing this vast in a universe that began as a nearly uniform soup of primordial energy? The leading theory is one of cosmic cannibalism, but on a scale that beggars belief. Perhaps the Bhuta's void isn't a single entity but the result of a merger. In the early universe, the cosmic web would have been peppered with many smaller voids, bubbles of lower density space. Like soap bubbles in a sink, these smaller voids would have drifted through space, and when they met, they would have coalesced, merging into a larger, more dominant bubble. As these bubbles expanded and merged, the space between them would be compressed. Matter, the galaxies and gas that found themselves on the borders of these expanding voids, would be squeezed together, their gravity amplified, forming the thick, luminous walls and filaments we see today. The void then is not merely empty space. It is an active agent in the formation of cosmic structure. It is the other half of the story. We live in the shining filaments precisely because the great voids pushed us here. The galaxies within its lonely tubular filament may be the last remnants of a smaller void wall that was swallowed whole during one of these ancient titanic mergers. They are the survivors of a cataclysm of emptiness their former neighbours long ago swept away to the distant shores of this dark cosmic ocean. This theory, while elegant, still strains the limits of our models. To create a super void of this magnitude requires the perfect alignment of conditions, a conspiracy of cosmic chance, that allow dozens, perhaps hundreds of smaller voids to merge into one Leviathan. It suggests a universe that is far more violent and segregated in its formation than we ever dared to imagine. It paints a picture of creation not as a gentle unfolding, but as a ferocious battle between matter and emptiness, where the voids push and shove, sculpting the universe we see today. They are the great unseen engines of cosmic architecture, their invisible influence defining where the great cities of galaxies can and cannot be built. And contemplating this place forces us to confront a profound sense of cosmic isolation. Imagine standing on a planet orbiting a star in one of those few lonely galaxies adrift in the centre of the Bhuta's void. Look up at your night sky, where we see a canvas dusted with the glittering light of the Milky Way and the faint smudges of 1,000 other galaxies. You would see nothing. Only the stars of your own galaxy would be visible. Beyond them, an unblemished, perfect and terrifying blackness would stretch out in every direction. From your vantage point, the universe would appear to be a single island of light in an infinite empty ocean. You might develop entire philosophies, entire religions based on the idea of your own cosmic solitude. You would have no reason to suspect that just beyond the reach of your telescopes 100 million light-years away, the rest of the universe blazed with the unimaginable light and fury. You would be utterly, completely and provincially alone, a prisoner of the great void. The discovery of this one gargantuan structure fundamentally altered our perception of the cosmos. It was the first proof that the universe's texture was not merely foamy, but that it could contain holes of a truly mind-altering scale. It was a scar on the face of the heavens, a testament to primordial processes we are only just beginning to comprehend. It forced us to accept that the empty spaces are just as important as the full ones, that they are the master sculptors of the grand design. But it also opened a new, more unsettling door. The Bhuta's void was the first of its kind to be found a monster hiding in our celestial backyard. But the universe is vast. If a void this large could form here, could there be others? Could there be structures even larger, even emptier, lurking in the unmapped depths of space? The confrontation with Bhutas was not an end to the story. It was the beginning of a hunt for even bigger ghosts, for the true titans of the cosmic dark. And the answer to that hunt would lead us to an even more profound revelation, to a place that would make even this supergiant void seem modest, a place that would challenge the very limits of what a universe can be. And so, we have stood at the precipice of this impossible emptiness, peering into a chasm of cosmic proportions. The sheer mind-numbing scale of the supergiant void, once a statistical ghost in the cosmic microwave background, is now a confirmed and terrifying feature of our universe. But to simply map its boundaries, to measure its diameter in billions of light-years, is to only chart the shoreline of a forgotten ocean. It answers the question of where, but it screams the question of why. How could the universe governed by the relentless pull of gravity allow such a wound to open in its otherwise luminous tapestry? How does 1 billion years of cosmic evolution result not in a crescendo of creation, but in this profound, echoing silence? To answer this, we can no longer rely on telescope lenses alone. We must journey to a different kind of cosmos, one born not of fire and fusion, but of logic and mathematics. We must step into the digital universes running inside our most powerful supercomputers. These are not mere animations, they are formidable scientific instruments. Within their silicon hearts, we can seed a universe from first principles, planting the quantum fluctuations measured in the afterglow of the Big Bang. We input the known ingredients, the precise amounts of ordinary matter, the dominant shadowy influence of dark matter, and the strange accelerating push of dark energy. Then we press a button that says run, and we watch 13.8 billion years of cosmic history unfold in a matter of weeks. And what emerges is breathtakingly familiar. We see the primordial gas begin to coalesce, drawn into unseen wells of dark matter. Tenuous threads begin to weave themselves into a magnificent glowing web. Galaxies ignite like embers, caught in a celestial draft, drifting along these filaments. pulled toward gravitational junctions where they merge and grow into colossal clusters. These simulations are our grand triumphs, a testament to how well we understand the cosmic dance of gravity and light. They produce universes that look, feel, and behave almost exactly like our own, with the correct distribution of galaxies, clusters, and smaller voids. Almost exactly. Because when we search these digital cosmos for an answer to the supergiant void, the simulations fall silent. They churn through quadrillions of calculations evolving countless possible universes, and they simply cannot build what we see. They produce voids, certainly, thousands of them, but they are modest bubbles in the cosmic foam, mere pockets of quietude between the bustling superhighways of the cosmic web. To find a region of this magnitude, this extreme and persistent emptiness is a statistical nightmare. The probability is so vanishingly small, it borders on the impossible, like finding a desert the size of North America in the middle of the Pacific Ocean. Our best models, the very pillars of modern cosmology, tell us that the supergiant void should not exist. It is an aberration, a ghost in the machine. The universe we observe contains a monster that the universe we have so carefully calculated is incapable of conceiving. This shocking discrepancy forces us back to the sky to stare once more into the abyss, but this time with a new, more penetrating gaze. The challenge is no longer just to confirm its existence, but to dissect its anatomy with a precision that leaves no room for doubt. We must move beyond a simple galaxy count and perform a forensic investigation of nothingness. This requires some of the most ambitious observational campaigns ever undertaken, a concerted effort to map the void's interior architecture, or lack thereof. Astronomers begin the painstaking process of three-dimensional cartography, using spectrographs to capture the faint light from the few lonely galaxies that wander within this great expanse. Each photon carries a barcode, a spectrum of light stretched by the expansion of the universe. This redshift tells us not only a galaxy's distance, but also its motion, allowing us to build a true 3D map of this desolate region. For years, they plot point after lonely point of light, and the picture that emerges is one of profound isolation of island universes, separated by gulfs of darkness so immense that they would have no knowledge of each other's existence. But the most crucial evidence lies not in the light we can see, but in the gravity we can't. We know that the vast majority of the universe's mass is dark matter, an invisible scaffolding upon which galaxies are built. Even if a region was strangely devoid of stars and gas, it should still be threaded with this immense unseen structure. Its gravity, though invisible, should still leave a footprint on the cosmos. Einstein taught us that mass warps the fabric of space-time, and that light must follow these curves. Distant galaxies whose light passes by a massive object on its way to us will appear slightly distorted, magnified, and sheared, a phenomenon known as gravitational lensing. It is our ultimate tool for weighing the universe, for seeing the unseen. So we point our telescopes through the heart of the supergiant void, looking for the telltale distortions of background galaxies whose light has made the billion-year journey across its breadth. We're searching for the gravitational signature of the dark matter that our theories insist must be there. And we find nothing. The light arrives almost completely unscathed. The background galaxies appear crisp, round, and undistorted. It is a gravitational flatline. This is perhaps the most unnerving discovery of all. The void is not just empty of things that shine, it is fundamentally, shockingly empty of the very substance that holds the universe together. The cosmic scaffolding itself has collapsed, or perhaps it was never built here at all. It is a true desert devoid of both water and the very bedrock beneath. This profound lack of matter provides the final critical key to unlocking the mystery of the CMB cold spot, the very anomaly that started this entire quest. For decades, the cold spot was a puzzle, a patch of the universe's baby picture that was just a little too cold, a little too out of place. Now, with the void mapped and its emptiness confirmed, we understand why. Imagine a photon of primordial light, a traveller from the dawn of time beginning its journey across the cosmos toward our telescopes on Earth. For most of its voyage, it passes through regions of average density. As it falls into a gravitational well created by a supercluster of galaxies, it gains energy, becoming slightly bluer, like a marble rolling downhill. As it climbs back out of that well, it loses the exact same amount of energy, becoming redder again, returning to its original state. The net effect is zero. But what happens when that photon encounters the supergiant void? It enters a vast, shallow gravitational basin. It still gains a little energy falling in. But during the billion years it takes to cross this expanse, the universe itself has been expanding, accelerated by the mysterious push of dark energy. This cosmic expansion stretches the void, making its gravitational well even shallower. So when the photon finally climbs out the other side, it has a much smaller hill to ascend than the one it rolled down. It doesn't lose all the energy it gained upon entry. The photon exits the void with slightly less energy than it started with. It is infinitesimally colder, and its wavelength is stretched ever so slightly. This phenomenon, the integrated Sachs-Wolf effect, is the fingerprint of dark energy acting across a colossal cosmic structure. The cold spot in the cosmic microwave background is the shadow of the supergiant void, cast across 13 billion years of space-time. It is the chilling receipt for a photon's journey through nothingness, a journey made longer and harder by the universe's own relentless acceleration. And here at this intersection of theory and observation, our understanding reaches a critical turning point. This is the moment the supergiant void transforms. It ceases to be a mere curiosity, a freakish outlier on a cosmic map. It becomes something far more important, far more dangerous to our comfortable theories. It becomes a crucible, a proving ground, a vast, silent laboratory where the fundamental laws of the universe are put to their ultimate test. Every major pillar of modern cosmology, our theories of how structures form the nature of dark matter and the overwhelming influence of dark energy, now faces a trial by emptiness. Our standard model of structure formation, which relies on the slow patient work of gravity over cosmic eons, is the first to be placed in the dock. This model is built on the idea that tiny primordial density fluctuations grew over billions of years, with overdense regions pulling in more matter and underdense regions giving their matter away. But for a region to become this empty, it would have had to start as an impossibly barren patch in the infant universe, a primordial hole far larger than anything predicted by our theories of cosmic inflation. Or it would require some unknown force, some cosmic blowtorch to have actively scoured the region, clean pushing matter out with an efficiency that gravity alone cannot explain. The void presents us with a stark choice. Either our understanding of the universe's initial conditions is wrong, or our understanding of how gravity builds the cosmos is incomplete. Next, we must confront the mystery of dark matter. The lack of gravitational lensing within the void is a direct challenge to its ubiquity. Dark matter is supposed to be the silent majority, the gravitational anchor around which all visible structure coalesces. Why is it missing here on such a cataclysmic scale? Did it behave differently in this patch of the universe? Is it possible that dark matter is not as cold and collisionless as we assume? Could it possess some unknown property, some faint interaction with itself, or other forces that allowed it to be expelled from this region? The void acts as a giant filter, and whatever passed through it or failed to tells us something new and profound about the substance that constitutes over 80% of the universe's mass. Its absence here is as loud as a supernova. Finally, we are forced to grapple with the most enigmatic force in all of physics: dark energy. In the dense, bustling filaments of the cosmic web, dark energy is a subtle background influence, a gentle cosmic tide pushing against the powerful grip of gravity. But here in this great gravitational desert, that balance is shattered. With almost no matter to provide a counteracting pull, dark energy's repulsive force may reign supreme. The supergiant void might not be a static relic of the early universe. It could be an active, growing entity being inflated from within by the very force that is accelerating the expansion of the entire cosmos. It may be a window into our ultimate future, a preview of a time when all structures will be pushed so far apart that the universe will become one vast, cold and empty void. This desolate landscape offers us our clearest view yet of the force that will ultimately decide the fate of everything. And so this colossal absence of matter forces upon us a profound re-evaluation. For nearly a century, our cosmology has been built upon a foundational assumption, a concept so central it is called the cosmological principle. It states that on the larger scales, the universe is homogeneous and isotropic. In other words, no matter where you are or which way you look, the universe should appear roughly the same. It is a principle of cosmic modesty, a declaration that there are no special places. The supergiant void stands in stark, silent defiance of this principle. It is an anomaly so vast that it challenges the very meaning of large scales. It suggests that our universe may not be the uniform, predictable place we imagined. Instead, it might be a place of wilder textures, of extreme peaks and unfathomable valleys, a cosmos more akin to a Jackson Pollock painting than a smooth, even canvas. This single, gaping hole in the fabric of existence threatens to unravel our most cherished assumptions about the nature of reality. The evidence is in. The measurements are confirmed. The simulations are broken. We find ourselves in a terrifying and exhilarating new era of cosmology. The abyss is not just a place on a map. It is a direct contradiction, a cosmic paradox served to us on a scale we can barely comprehend. The comfortable story we told ourselves about how the universe works has a chapter missing a billion light-year-wide hole in the narrative. To explain this hole, to fill this void in our understanding, we can no longer tinker at the edges of our theories. The data now demand something more, something radical. We are being forced by the sheer stubborn emptiness of it all to contemplate ideas once relegated to the fringes of science, to ask questions that challenge the very definition of our universe. And so we are left suspended here in the heart of this profound silence. The scale of the Buddha's void, now fully comprehended, has transitioned from a geographical curiosity into a deep philosophical problem. It's one thing to chart an empty space on a map of the cosmos. It is another thing entirely to have to explain its right to exist. This celestial wound, this sprawling emptiness carved out of the universe, refuses to be a passive feature of the cosmic landscape. Instead, it poses an active, insistent question to the very foundations of cosmology. How do you create nothing on such a magnificent scale? How does the universe, governed by the relentless pull of gravity, a force dedicated to gathering, to clumping, to building, allow for such a spectacular failure of its primary directive? The first, most intuitive answer that emerged from the minds of cosmologists is a theory born of elegant simplicity, an idea of cosmic cannibalism. This is the void-in-void hypothesis, a story of assembly, not by addition but by subtraction. Imagine the early universe not as a smooth, uniform fabric, but as a churning, frothy foam of cosmic potential. In this primordial state, smaller pockets of low density would have naturally formed little bubbles of emptiness destined to grow. Gravity, the universe's great shepherd, works in two directions. While it pulls matter together to forge stars and galaxies in denser regions, its absence in these underdense bubbles has the opposite effect. The meagre bits of matter inside a fledgling void are pulled outwards by the gravitational might of the denser regions surrounding them, evacuating the space, making it emptier still. This process creates a feedback loop. The emptier a void becomes, the more effective it is at banishing what little remains within its borders. Over hundreds of millions of years, these nascent voids would have begun to expand. Now picture these individual bubbles, these growing pockets of nothingness, drifting through the cosmic ocean like raindrops on a vast dark window pane. As the universe expands, pulling everything apart, these voids also stretch and grow. Inevitably, two expanding voids would touch. Their borders' thin walls, where a few lonely galaxies might reside, would dissolve. The two voids would merge their individual emptinesses, combining to form a larger, more imposing barrenness. Like tributaries feeding a great river, countless smaller voids, each one a story of gravitational failure, millions of light years across, could have coalesced over the grand sweep of cosmic time. They would have flowed into one another, their boundaries dissolving, their collective emptiness pooling together to sculpt a single monstrous chasm. This process, a slow and silent merger of absences over billions of years, presents a plausible, almost poetic explanation for the Buddha's void. It wouldn't be a single anomalous event, but the final mature state of a process that began with the universe's first breath. You're looking at the universe's greatest excavation project, dug not with a shovel, but with the patient, persistent force of gravity's neglect. This elegant idea finds powerful support when we pull our gaze back and look at the void's immediate surroundings. An emptiness this profound cannot exist in isolation. The matter that should be here, the thousands of galaxies missing from this cosmic census, had to go somewhere. And it did. Encircling the void like a cliff face bordering a great canyon are some of the most magnificent structures in the known universe. We see the Hercules supercluster, the Corona Borealis supercluster, and the immense sprawling structure known as the Great Wall. These are not merely its neighbours, they are its consequence, the very material displaced and organised by the void's relentless gravitational deficit over eons. One cannot exist without the other. The void is the whole, but the Great Wall is the excavated Earth piled high at its edges. The galaxies within these superstructures are packed together more tightly than the cosmic average, forming dense luminous rivers of light. They are the cosmic refugees, a population of galaxies pushed and pulled over billions of years, squeezed into these filaments by the expansion of the void behind them. This symbiotic relationship between the colossal emptiness and the colossal structures is a cornerstone of our understanding of the cosmic web. The universe, it seems, is a grand tapestry of checks and balances. For every action a reaction, for every great void a great wall. It's a powerful, compelling picture, one that fits neatly into our models of how large-scale structure should form. The merger of smaller voids created the supervoid, and the matter evacuated from them was swept up like cosmic dust, forming the brilliant galaxy-rich walls that frame it. It feels right. It feels complete. But this explanation, as satisfying as it is, only describes the mechanics of the process. It tells us how the void was assembled, but it doesn't tell us why the initial seeds, the smaller voids, were there in the first place. To answer that, we have to travel back in time, back beyond the first stars, beyond the first galaxies, to a moment when the entire observable universe was smaller than a single atom. We must journey to the era of cosmic infancy, just fractions of a second after the Big Bang. Here in this crucible of creation, the universe was an almost perfectly smooth, unimaginably dense and hot soup of fundamental particles. Almost perfect, but not quite. Quantum mechanics. The strange and ghostly rulebook of the subatomic world dictates that on the smallest scales there is no such thing as true calm. There is always a roiling, unpredictable fizz of energy, a phenomenon known as quantum fluctuations. These were unimaginably tiny jitters in the density of the primordial universe, microscopic regions that were infinitesimally denser or less dense than their surroundings. Then, in an event known as cosmic inflation, the universe expanded exponentially, stretching from the subatomic to the macroscopic in a sliver of a second. This violent expansion grabbed those tiny quantum fluctuations and blew them up to astrophysical proportions. The slightly denser regions became the gravitational seeds around which matter would later clump the fertile ground from which all future stars and galaxies would sprout. The slightly less dense regions were equally important. They were the seeds of cosmic deserts, the predestined locations of the great voids. The Buddha's void, in this view, is not an accident of cosmic history. It is an inheritance. Its destiny was written into the fabric of space-time a mere 10 to the minus 36 seconds after the beginning of time. It is the ultimate magnificent expression of a single unlucky quantum flutter. This deep connection to the earliest moments of creation is further illuminated by one of the most subtle and beautiful phenomena in cosmology, baryonic acoustic oscillations, or BAOs. Think of the early universe before the first atoms formed. It was a sea of plasma, a dense opaque fog of charged particles and photons of light all coupled together. Within this plasma, the battle between gravity pulling inward and radiation pressure pushing outward created immense sound waves, ripples of pressure propagating through the primordial soup. These were not sound waves you could hear, but waves of density, a cosmic drumbeat resonating through the infant universe for its first 380,000 years. Then suddenly the universe cooled enough for protons and electrons to combine, forming the first neutral hydrogen atoms. The fog cleared. This moment, known as recombination, is when the cosmic microwave background was released, the universe's baby picture. At that instant, the sound waves abruptly froze in place. The outward propagating shells of denser matter, the crests of these cosmic ripples, were locked into the fabric of space. They left behind a ghostly spherical signature, a sphere of slightly higher density surrounding a center of slightly lower density. This signature is a standard ruler for cosmologists, a preferred distance imprinted on the universe, and it provides a powerful mechanism for creating voids. The center of each of these primordial sound waves was a naturally underdense region, the perfect seed for a void. As the universe evolved, gravity would enhance this effect, pulling matter toward the denser shell and away from the emptier center. This theory beautifully explains why many voids we observe tend to be roughly spherical. They are the faint colossal echoes of a sound that fell silent 13.8 billion years ago. The spherical shape of the Bhuta's void, one of its most perplexing features, at last seems to have a natural explanation. It is a fossilized sound wave from the dawn of time. Here, with these powerful theories in hand, merging voids, quantum fluctuations and cosmic sound waves, we should be able to close the book on the Bhuta's void. We have a complete narrative from a quantum seed to a modern-day supervoid, flanked by the superclusters it helped build. Our models, the sophisticated computer simulations that represent our best understanding of the cosmos, can replicate this process. They can grow voids. They can build cosmic webs. We give the simulation the initial conditions dictated by the Big Bang. We input the laws of physics as we know them, and we let it run for 13.8 billion years of simulated time. And this is where the story takes a sharp, unsettling turn. This is where the Bhuta's void stops being a confirmation of our theories and starts to become a terrifying exception. Our simulations do indeed produce voids. Lots of them. They even produce large voids through the merger process we envisioned. But they do not produce this. The standard model of cosmology, a framework of breathtaking predictive power, the same model that accurately describes the cosmic microwave background and the distribution of galaxies on most scales, simply cannot account for Bhutas. It is a statistical impossibility. A ghost in the machine? To get a void this large, this empty, and this perfectly spherical, our simulations would need far more time than the universe has actually had to exist. The slow, patient process of merging smaller voids and evacuating matter, even starting from the best possible quantum seed, is not efficient enough to create a structure of this magnitude in just 13.8 billion years. The universe, according to our own rulebook, is too young to have built this place. It's like finding a towering 1,000-year-old redwood tree in a forest that you know was only planted a century ago. The evidence of your eyes contradicts the inescapable logic of your timeline. The void's profound sphericity, which the baryonic acoustic oscillations seem to explain so well now, becomes part of the problem. While BAOs explain the origin of spherical voids, the process of multiple random mergers should have destroyed that pristine shape. When voids of different sizes and shapes coalesce, the resulting supervoid should be irregular, lumpy and oblong, bearing the scars of its violent chaotic formation. Yet the Bhuta's void is hauntingly spherical. It's too big, too empty, and too perfect. It's as if the universe used a celestial compass to draw a perfect circle, 330 million light-years in diameter, and then meticulously erased everything inside. This single object, this magnificent absence, throws a wrench into the gears of our grand cosmological machine. It suggests that something is missing from our understanding. Perhaps the initial density fluctuations in the early universe were not as simple as we believe. Maybe there's a nuance to the nature of dark energy, the mysterious force driving cosmic acceleration that makes void growth far more aggressive than our models predict. Or perhaps, and this is a far more disturbing thought, our theory of gravity itself, Einstein's general relativity, is incomplete on these immense scales. The void is no longer just a hole in the cosmos. It has become a hole in our knowledge, a vast empty space in the very center of our most successful scientific theory. Its silence is deceptive. For those who know how to listen, it is screaming at us, telling us that the story of the universe is stranger, more complex, and far more mysterious than we have ever dared to imagine. It forces us to confront the possibility that the emptiness is not empty at all, but is instead filled with the clues to a new undiscovered physics. And as we stand here, humbled by its scale and perplexed by its existence, we must now venture beyond the comfort of established science. We must begin to explore the radical, the speculative, the seemingly impossible ideas that this cosmic giant demands we consider. Faced with an abyss that defies our models, a chasm in the cosmos that whispers of a broken physics science had to confront a terrifying possibility. Perhaps the standard model of cosmology, our greatest intellectual achievement for understanding the universe, was not just incomplete but fundamentally wrong. For decades we had constructed a beautiful, elegant story of creation, one that began with a fiery birth cooled into matter and was sculpted by gravity into the luminous cosmic web we see today. But the supergiant void, in its stark, cold and monolithic emptiness, refused to fit within that story. It was a statistical impossibility, an outlier so extreme it felt like a deliberate challenge to our cosmic narrative. A void of this magnitude, this profound nothingness, simply should not exist in a universe governed by the rules we thought we understood. It was as if we had spent a century meticulously assembling a colossal, intricate clockwork mechanism, only to discover a gear inside so vast it should have shattered the entire machine from the very beginning. This was the crisis point, the moment where the map of reality no longer matched the territory. The familiar comfort of our equations gave way to a chilling uncertainty, forcing us to ask a question that strikes at the very heart of our existence. What is the true nature of the force shaping our universe's destiny? The answer cosmologists now believe was hiding in plain sight, concealed within the very emptiness we found so disturbing. It was a phantom that had haunted our equations for decades, an unseen presence whose influence we could only infer. We call it dark energy. It is not energy in any classical sense. It is not light nor heat, nor the kinetic fury of a supernova. It is something far more ethereal, more fundamental. You can think of it as a property of space itself, an intrinsic uniform pressure woven into the vacuum, a cosmological constant. And unlike gravity, which pulls everything together in a relentless cosmic embrace, dark energy does the opposite. It pushes, not with an explosive force, but with a subtle, insidious and ever-present insistence. It is the universe breathing out an inexorable expansion that gains strength as space itself expands. For billions of years, gravity was the undisputed champion of the cosmos, corralling matter into stars, galaxies, and the great filaments of the cosmic web. But all the while, dark energy was playing a longer game. As galaxies flew further apart, gravity's grip weakened over these vast distances. Dark energy, however, grew stronger. With more space, there was more of this vacuum energy, more of this outward push. The universe's expansion, which should have been slowing down, began to accelerate. Now look again at the supergiant void. It is precisely because it is so empty that it becomes the ultimate theatre for this cosmic battle. Inside the glittering filaments of the cosmic web, the fight is a chaotic melee. Gravity is strong there, a local tyrant pulling gas clouds into stars and galaxies into clusters. Dark energy's subtle push is almost entirely overwhelmed, lost in the gravitational noise. But out here in the unfathomable quiet of the great void, there is almost nothing for gravity to grab onto. The density of matter is so low that gravity's voice is but a faint whisper. And in this silence, the persistent hum of dark energy becomes the dominant sound. It is here in the near-perfect vacuum that this mysterious force can act unimpeded, revealing its true nature. The void isn't just empty because it was born that way. It is actively becoming emptier. Dark energy, this anti-gravitational ghost, is pushing its boundaries outward. It stretches the space within it, relentlessly shoving the few galaxies that remain toward the dense walls of the surrounding filaments. The supergiant void then is not a static feature. It is a dynamic growing entity, a cosmic lung that is inflating with every passing moment. Studying this process offers us a unique, unprecedented window into the deepest mystery in all of physics. By measuring the rate at which the void expands, by observing the subtle motions of the galaxies on its periphery being swept away like debris on a rising tide, we can directly measure the strength of dark energy. We can test its properties with a precision impossible anywhere else. We can ask, is this energy truly constant as Einstein first proposed, or does its strength change over time? A changing dark energy would have profound implications, suggesting a new unknown physical field permeating the cosmos, a quintessence that could dictate the universe's ultimate fate. In the crowded cities of galaxies, these clues are hopelessly buried, but the void acts as a colossal magnifying glass, taking the minuscule effect of dark energy and amplifying it across 1 billion light-years. It transforms this ethereal cosmic whisper into a roar we can finally begin to decipher. the very feature that seemed to threaten our understanding of the universe has, in a stunning reversal, become our most powerful tool for completing it. The void's emptiness is not a flaw in our theory. It is the key to unlocking the truth about the force that will govern our cosmos for all of eternity. It is the pristine canvas upon which the future of everything is being painted. But how could we be sure? How could we prove that this delicate interplay of gravity and dark energy could truly conspire to create a monster like the supergiant void? Observing it was one thing. Explaining its genesis was another challenge entirely. The solution would require a new kind of experiment, one conducted not in a sterile laboratory on Earth, but inside the most powerful supercomputers ever built. The goal was audacious, almost hubristic in its ambition to create a new universe from scratch, to simulate the entire 13.8 billion year history of cosmic evolution, from the faint quantum flickers after the Big Bang to the intricate galactic tapestry of the present day, and see if a structure like the void could naturally emerge. These are not mere animations. They are among the most complex calculations ever undertaken by humanity. Scientists begin with a vast virtual cube of space, sometimes billions of light years on a side. Into this digital crucible they pour the fundamental ingredients of our reality, measured with exquisite precision from observations of the cosmic microwave background. They seed it with the primordial density fluctuations, the tiny, almost imperceptible variations in the temperature of the infant universe. These seeds are the ancestors of everything we see today. Then they add the matter and energy. A small fraction, about 5%, is the familiar atomic matter of stars, planets, and ourselves. A much larger portion, around 27%, is the invisible scaffolding of the cosmos dark matter. This mysterious, non-luminous substance provides the gravitational anchor around which galaxies form. And finally, the crucial dominant ingredient, nearly 70% of the total energy budget, is assigned to dark energy, the very force we seek to understand. With the ingredients in place, the simulation is set in motion. The only law is gravity as described by Einstein's equations, pitted against the relentless push of dark energy. The computer then begins to calculate the gravitational pull between trillions of virtual particles, step by painstaking step, advancing cosmic time by millions of years with each tick of its computational clock. What unfolds is a breathtaking spectacle, a digital Genesis story playing out on a cosmic scale. For the first few 100 million years, the universe is a nearly uniform, foggy expanse. But soon, the gravitational seeds begin to sprout. Regions that started out just a fraction of a percent denser than average begin to pull in more and more dark matter. We watch as the first gossamer-thin sheets of matter collapse, forming vast, two-dimensional walls. Where these walls intersect, long, brilliant filaments are born, snaking through the simulated cosmos like the luminous threads of a celestial nervous system. And at the nexus points of these filaments, where the rivers of matter converge, dense knots form and ignite. These are the halos of dark matter, where the first galaxies begin to blaze into existence like celestial campfires lit in the immense darkness. The cosmic web in all its intricate glory builds itself before our eyes. But as the structure grows, something else is happening. The regions that began with slightly less density than average are losing the gravitational race. As their denser neighbours greedily pull matter away, these underdense regions become more and more desolate. They are the cosmic valleys from which all the rivers of matter flow, and they are being bled dry. This is where dark energy begins to assert its dominance. Within these nascent voids, the outward push of the vacuum meets little resistance. They begin to swell, their expansion accelerating. They merge with one another, their boundaries dissolving as they coalesce into larger and larger empty domains. The filaments are squeezed, the galaxy clusters compacted as the voids grow to become the true volume holders of the universe. For years, these simulations, while astonishingly successful at recreating the cosmic web, had a persistent problem. They could create voids, certainly, but they could not create anything on the scale of our supergiant void. The simulated universes looked statistically correct, but they lacked the magnificent, terrifying monsters of the real cosmos. The models were too tame. This failure was itself a profound clue. It suggested that either our initial conditions were slightly wrong, or more tantalizingly that our understanding of the physics of gravity or the nature of dark energy was still missing a crucial piece. Teams around the world refined their models, tweaked the parameters, and harnessed ever more powerful computers. They ran thousands of digital universes, each with a slightly different recipe, in a grand search for the one that matched reality. They experimented with different flavors of dark energy, some that grew stronger over time, others that weakened. They even cautiously explored modifications to Einstein's theory of gravity over vast distances, wondering if its pull might be slightly weaker in the great voids than our equations predict. It was a colossal effort of trial and error, a search for the cosmic ghost in the machine. And then breakthroughs began to happen. With simulations of unprecedented scale and physical fidelity, like the illustrious TNG and Millennium projects, they finally saw it. By refining their models of galactic feedback the way gargantuan black holes and exploding supernovae can blast gas and matter out of a galaxy, they discovered a powerful mechanism for void building. These explosive cosmic events, acting like celestial blowtorches, could evacuate vast regions of space far more efficiently than gravity alone, effectively giving the voids a head start in their growth. In these new, more sophisticated digital universes, the voids began to swell to monstrous proportions. After billions of years of simulated evolution, structures began to emerge that bore a striking resemblance to the supergiant void. They were vast, they were empty, and when the light from the simulated cosmic microwave background was passed through them, it produced the telltale signature of a cosmic chill, a digital cold spot. The impossible object had been rendered possible. The simulations proved that under the right conditions, our current model of the universe, with its strange brew of dark matter and dark energy, could forge such a magnificent desolation. The void was not an error message. It was a natural, if exceptionally rare, consequence of the fundamental laws of our cosmos. This success did more than just explain a single anomaly. It transformed our entire perception of cosmic emptiness. The supergiant void and the digital twins we had created for it became the ultimate proving ground for our theories. Because its interior is so simple, so devoid of the messy complications of stars and galaxies, it acts as a perfect laboratory for testing the laws of physics in their purest form. Within its boundaries, we can study gravity in a regime found nowhere else. Einstein's theory of general relativity has passed every test we have thrown at it within the solar system and in the dense environments of galaxies. But does it hold true over the billion light-year expanse of a near-perfect vacuum? Some alternative theories of gravity propose that the fabric of space-time might be slightly more pliable, slightly less rigid in these incredibly low-density environments. If so, light travelling through the void might be deflected in ways subtly different from what Einstein predicts. The paths of the few galaxies inside might deviate from their expected trajectories. The void therefore becomes a colossal gravitational lens, and by studying its effects with extreme precision, we can place the tightest constraints yet on the fundamental theory of gravity that governs our entire universe. We can also use it to test the very nature of dark matter. Is it truly cold and collisionless as our models assume, or does it have some faint undiscovered interactions that only become apparent over immense scales? If dark matter particles could decay or annihilate over cosmic timescales, the void would be the first place we would see the evidence, a place free from astrophysical noise. The void is a filter stripping away the complexities of the cosmos and leaving us with only the most fundamental forces and particles to observe. Every photon that crosses it, every galaxy that skirts its edge becomes a messenger carrying information from a pristine laboratory the size of 1,000 Milky Ways. The apparent tension between the void and the cosmic microwave background, the puzzle of the cold spot, has been recast. It is no longer just a problem but an opportunity. The subtle gravitational effects within the void, known as the integrated Sachs-Wolf effect, are exquisitely sensitive to the properties of dark energy. The coldness of that spot on the sky is now a dial, allowing us to tune our cosmological parameters with breathtaking accuracy. A slightly colder spot might imply a slightly stronger dark energy. A warmer one could point to a subtle modification of gravity. The void forces our theories to be accountable, demanding a precise quantitative explanation for every minute detail. We have come full circle. We began by staring into an abyss, a place defined by absence, a terrifying hole in our map of existence. We saw it as a violation, a monstrous anomaly that threatened to undo everything we thought we knew. But with each new discovery, each refined simulation, our perspective has been profoundly transformed. We have learned to read the language of nothingness, to see the intricate physics encoded in the emptiness. The supergiant void is not the absence of creation. It is a fundamental structural pillar of the cosmos, as vital to its architecture as the brightest supercluster of galaxies. It is the arena where the ultimate cosmic struggle between gravity's embrace and dark energy's relentless push is laid bare for us to see. It is a cosmological gyroscope, its immense slow rotation, tracing the subtle torques of primordial forces. It is a time capsule, preserving a pristine record of the universe's initial conditions in its near-perfect vacuum. Far from being a flaw in the grand design, the void has revealed itself to be the grandest of all laboratories, a silent, empty stage where the fundamental forces of nature perform their final, dramatic act, shaping the ultimate destiny of our universe. And so, we arrive at the edge of our own journey. We have travelled across an almost unimaginable gulf of space and time, from that first bewilderingly cold patch in the afterglow of creation to the profound billion light-year chasm we now know as the supergiant void. We began with a simple question, a cosmic anomaly that defied our neat models, a whisper of imperfection in the otherwise smooth symphony of the Big Bang. It was a puzzle that could have been a glitch, an observational error, a statistical fluke destined to be forgotten in the annals of astronomy. But it stubbornly refused to vanish. Instead, it beckoned us forward, pulling us deeper into the great cosmic ocean, forcing us to confront the true staggering scale of the universe we inhabit. What we found there, or rather, what we didn't find, has forever altered our map of reality. This void is not merely a place, it has become a new kind of lens, a unique celestial instrument for interrogating the universe's most elusive secrets. For decades we studied the cosmos by what was there, the brilliant blaze of galaxies, the intricate filaments of the cosmic web, the gravitational might of massive clusters. We built our understanding on substance, on light, on presence. The supergiant void taught us a profound and paradoxical lesson that sometimes the most revealing answers are found in the absence of things. The emptiness itself has a story to tell, a story written in the subtle curvature of space-time, in the ancient light that has traversed its depths, and in the very structure of everything that surrounds it. It has served as a crucible for our most cherished theories, testing them against an extreme reality we never predicted. Think back to the great invisible skeleton of our universe, dark matter. We had imagined it as a pervasive gentle scaffold, a cosmic garden trellis, upon which the luminous vines of galaxies would patiently grow over billions of years. Our simulations produced beautiful web-like structures, and for the most part they matched observation. But they struggled to create an emptiness so vast, so complete, so utterly definitive as this one. The supergiant void presents a formidable challenge to our standard models. Its existence suggests that the processes governing cosmic structure might be more dramatic, more violent, or perhaps just different than we had ever conceived. Is there a property of dark matter we have failed to grasp? Does it possess some form of self-interaction, a faint internal pressure that helps it evacuate from certain regions with an efficiency our computers cannot replicate? Or is the answer even more profound, hinting at modifications to gravity itself on the larger scales? The void, by being so utterly empty, has become a laboratory for the unseen. The faint gravitational lensing of distant galaxies around its perimeter, the subtle distortions of light from the far side of the universe, are the only tools we have to trace the banks of this invisible river of nothingness. Its stark, well-defined edges are like the chalk outline of a missing giant, allowing us to probe the fundamental nature of the 95% of the cosmos that remains stubbornly, maddeningly dark. This chasm forces our theories to be better, to be more robust, demanding an explanation not just for the great cosmic cities, but for the vast and silent wildernesses that lie between them. And then there is the ghost that haunts all of modern cosmology, dark energy. For years it was a phantom in our equations, a fudge factor, a placeholder for the unknown force driving the accelerating expansion of the universe. It was a concept born from the light of dying stars in distant galaxies, a theory built on the assumption that those stellar explosions were reliable cosmic mile markers. The evidence was compelling, but it was indirect inferential. We needed something more, a different kind of proof, a new line of inquiry. And the supergiant void, in a spectacular convergence of theory and observation, provided it. The connection we traced between the void and the cosmic microwave background's cold spot is perhaps one of the most elegant and startling discoveries of the 21st century. It transformed this empty space from a mere curiosity into a key piece of evidence for the active dynamic and changing nature of our universe. Let us revisit that epic journey of a single photon of light. Imagine it a messenger from just 380,000 years after the Big Bang, travelling uninterrupted for over 13 billion years on its way to your eye. As it approached the supergiant void, it fell into its subtle gravitational well, gaining a tiny amount of energy, a minuscule blue shift like a marble rolling downhill. For the next 300 million years, it crossed this vast emptiness. Finally, it had to climb back out, fighting against the gravity of the surrounding structures, a journey that should have cost it the exact same amount of energy it had gained on the way in. In a universe without dark energy, the photon would emerge unchanged. The blue shift in the red shift out a perfect cancellation. But our universe is not so simple. During the immense time our photon spent inside the void, the universe itself was stretching. The inexorable push of dark energy was accelerating the expansion of space. The gravitational hill our photon had to climb on its way out was now shallower, less steep than the one it had descended on its way in. The expansion of the cosmos had flattened the landscape. Consequently, it didn't have to expend as much energy to escape. It left the void with a tiny net surplus of energy compared to its neighbours that didn't cross such a chasm, appearing to us as ever so slightly hotter or younger. But from our perspective, looking back through the void, the effect is opposite. The light from behind is stretched, losing energy, making that patch of sky seem colder. This phenomenon, the integrated Sachs-Wolf effect, is no longer just a theoretical quirk. It is a measurable signature, a faint thermal fingerprint left upon the oldest light in existence, a testament to the fact that the very fabric of space-time is alive and dynamic. The void ceased to be just an absence of matter. It became a cosmic dynamometer measuring the persistent repulsive force of dark energy at work across cosmic history. It is a direct confirmation, written in the cold light of the early universe, that the cosmos is not just expanding, but that the expansion is speeding up, driven by a substance whose ultimate nature remains the single greatest mystery in all of science. This journey has reshaped our very perception of the cosmic architecture. We once saw the universe as a relatively uniform distribution of matter, punctuated by galaxies and clusters like lights in a sprawling city at night. Now we understand the profound importance of the darkness in between. The cosmic web is not a web filling a void. The web and the voids are two sides of the same coin, a yin and yang of cosmic structure co-evolving, shaping one another through gravitational interplay. The voids are not passive emptiness. They are active environments. Their immense outward-pressing low density sculpts the filaments and superclusters around them, herding galaxies into the great cosmic rivers and walls that define the large-scale structure. They are the unseen currents and prevailing winds of the cosmic ocean, dictating where the islands of matter can form and where they cannot. To understand the web, we have learned, we must first understand the void. To comprehend the breathtaking complexity of cosmic structures, we must first appreciate the staggering simplicity of their absence. This understanding represents a fundamental maturation in the science of cosmology, a shift from seeing the universe as a collection of objects to seeing it as a single interconnected evolving ecosystem of matter, energy and space-time. And in this grand unfolding narrative, what is our role? We are the universe made conscious, the pattern on the loom that has learned to see itself. The discovery of the supergiant void is not just a scientific achievement, it is a profoundly human story. It is a story of persistence of scientists like Rodnick Brown and Williams, who trusted their data even when it pointed to something unbelievable. It is a story of intellectual courage, of refusing to dismiss an anomaly, of seeing a potential discovery where others saw only a problem. This quest reminds us that our place in the cosmos is defined not by our physical size, but by the reach of our curiosity and the power of our intellect. From this tiny fragile planet orbiting an unremarkable star in a quiet corner of the Milky Way, we have mapped a structure so large that light itself takes 1 billion years to cross it. We have detected its subtle influence on the echo of the Big Bang. We have used it as a tool to weigh the darkness and measure the expansion of reality. There is a humbling and yet empowering beauty in that realization. We are ephemeral, fleeting creatures on a cosmic timescale, yet we have been able to piece together a coherent story of the universe's past, present and future. Our story, however, is far from over. The supergiant void, for all it has taught us, still holds its deepest secrets close. The questions it has answered are matched only by the new ones it has raised. Is it a singular object, a unique feature of our cosmic neighbourhood, or are there other, perhaps even larger voids lurking in the unmapped territories of the cosmos? As we speak, a new generation of cosmic cartographers is preparing to find out. Telescopes, like the Vera C. Rubin Observatory in Chile, will soon begin a decade-long survey, the legacy survey of space and time mapping the southern sky with unprecedented depth and speed. It will create the most detailed three-dimensional map of the universe ever attempted, cataloguing billions of galaxies, and by extension the voids that separate them. From space, the Euclid and Nancy Grace Roman telescopes will join the hunt, using their exquisite sensitivity to weak gravitational lensing to trace the invisible scaffolds of dark matter with breathtaking precision. They will not just find voids, they will dissect them. They will measure the distribution of the few lonely galaxies that drift within their confines. They will map the sharpness of their boundaries and test our cosmological models to the breaking point. Will these future observations confirm our current understanding, or will they reveal new complexities, new surprises that send us back to the drawing board once more? That is the thrilling, tantalizing promise of science. The end of one journey is always the beginning of another. We are left finally with a profound sense of awe. The universe is not just stranger than we imagine, it is stranger than we can imagine. It is a place of brilliant quasars that outshine entire galaxies of neutron stars spinning with the precision of atomic clocks of black holes that warp the very fabric of space-time. And yet it is also a place of quiet, humbling, majestic emptiness. The supergiant void is a monument to the power of gravity and time, a natural cathedral of cosmic proportions, carved out over 13 billion years. It stands as a stark and beautiful reminder that the universe is under no obligation to be filled, no obligation to meet our expectations of what it should be. It simply is. Our great privilege and our great adventure is to witness it, to listen to its silent stories, and to try, however imperfectly, to understand. The great cosmic tapestry is woven not only with threads of light, but with threads of darkness, and it is in the interplay between the two, in the grand design of presence and absence, that we may finally glimpse the true and complete picture of our magnificent and astonishingly empty universe. The quest continues.